In the instant that you're trying to solve a differential equation using the process for exact equations, but you found out that our equation is actually a non-exact equation, we are going to use a different method. Probably we're just going to duplicate a series of methods for solving exact equation, but for us to be able to use that, we need to identify the integrating factor for non-exact equations. As you can remember, when we're trying to solve linear equation, we use the concept of integrating factor that will be multiplied in both sides of the equation, the original equation, so that we can actually identify the process or make it simpler in solving for the solution. Similar here, we have integrating factor for non-exact equations. But take note that for the identification of non-exact equation follows with, if you're given with here this equation where you have m of xy dx and you have your n of xy dy. But then again, you were not able to establish the partial derivative of m with respect to y is actually not equal to the partial derivative of n with respect to x. You were not able to establish this because this is actually the criterion for the given equation to be exact. So this is clearly a non-exact equation. Now, our integrating factor will allow us to make use of our given equation and probably transform it to another form where we can actually use the process of solving exact forms or exact equation for the result. Okay, so how do we do that? How do we identify the integrating factor? Actually, again, as mentioned, you're going to multiply here an integrating factor on your m dx, also multiplying that on our n dy. N is a short way of writing that function as well as this one here, equal to the integrating factor times 0. But of course, multiplying that is just equal to 0. So you would like a form in this manner. Now, we call this integrating factors because there are two possibilities. The first integrating factor that we are going to use, okay, is actually identified as integrating factor in terms of our function x, mu of x. As mentioned in our integrating factor for linear equation, it actually has the same formula, but in this case you have here e to the power of the integral. In the linear equation, we actually used p of x, but since p here is not clear, so we'll have here the form of f of x dx. Okay, so this is actually one of the possibilities. The second one, okay, is actually mu of y. So we can actually have two different forms here as long as what you're multiplying here will also be the same on the other side. But mu of y will be equivalent to the e to the negative of the integral of f of y dy. Okay, so notice that our mu of y will have a negative exponentiation, okay, unlike our mu of x. Now, how are these two different? Okay, these two are actually different because of this. If we're talking about the first method, our f of x, okay, to be integrated with as an exponent of our e is actually equal to this notation. F of x is actually equal to 1 over your n, or n of xy, similar to that, okay, whatever that function is, times, you will have here the partial derivative of your m with respect to y, okay, minus the partial derivative of your n with respect to x. Now notice, these two are similar to that, and of course, if this is actually exact, this is 0, that means we don't need the integrating factor because you will have 0 here, 0, so basically, you will have a different form. Okay, you will just have any value of c, right, for our integral of 0. Okay, so that is what will happen if it's exact. But if it's not exact, we'll have this form here. This will only be possible if whatever the result of this is a function of x. So if it is a function of x, so we can use this integrating factor to be multiplied in our equation, original equation, to solve it in the form of exact process. Okay? We also discuss a video for that. We have a video for that discussing the process of solving exact equations. Okay? So again, the purpose of integrating factor is to make the non-exact exact by the use of an integrating factor using this. Now, if in the instance that this is not equivalent to a function of x, take note that a function of x means it is an expression, algebraic expression, or a function with only x as a variable? What if when you express it this manner, it has y, so that means our first integrating factor is not possible. Now, we can use the second form here if we have here our f of y intended for the integral here is actually equal now to 1 over m, and then you have your same item here, okay? Partial derivative and with respect to x. Again, similarly, this is not 0 because we are sure that it's non-exact. So if this entire form will become a function of y, so we can use this second as an integrating factor to be multiplied in our given equation. And later on, once we multiply that, we are going to duplicate the process of solving the exact method. Okay, the method for exact equations. Okay. Now, what if both of these two are good? Meaning, in this form, we can get a function of x. In this item, we can get a function of y. So you can actually use either of them. Okay. So you need to verify it carefully, because in the instant that none of them would fit the criteria for integrating factor, so we might need another method as well in solving for this given equation. Now we will have a summary of steps of solving non-exact equations, just to compare it with a summary of solutions or process of solving exact equations. We will have that in a separate video. Thank you very much for watching.